Welcome to the historical heart of Rolls Royce engine manufacturing. We're here in Derby, Northern England at the Rolls Royce site, which is massive and comprised of various different facilities doing various aspects of engine maintenance, testing, final assembly, training, you name it. Here, we're in the final assembly line, a global supply chain process where components come and go between sites all over the world and end up right here. This is the only place in the world where these Rolls-Royce engines do their last final assembly before they're shipped out to customers. Today we're going to be looking at various aspects of what Rolls-Royce is doing here, but especially at the Trent 1000, which is the Trent that is powering 787s, and how they've been working through some of the durability issues, fixing them up, getting them in and back out to customers so they can last longer for them, as well as refining the way they build these new and creating new versions that will give airlines more time on wing. And we'll get to learn about some of the really nice, detailed, technical aspects of what goes into that. Hopefully see some parts of engines that maybe we haven't seen before, at least I haven't. Let's go spend the day with Rolls-Royce here in Derby. This site here goes back to 1907. That was the beginning of when this was constructed and production first started. The kind of advances over time in what they've been building here, the technology, is just mind-boggling to think of going back to then and seeing what's happening here now.
I currently lead the Trent 1000 task force, who have been charged with delivering the product improvements and the fleet health recovery for the Trent 1000. We are introducing some durability enhancements onto the engine, and we're doing that in two phases. So the phase one durability enhancement introduces chiefly a 40% cooling flow improvement to our high pressure turbine blade in the hot end of the engine. What that does is essentially double the time on wing. Phase two then offers up an additional 30% time on wing through the HP turbine blade also, and that's achieved through weight reduction of the high pressure turbine blade itself, which essentially reduces the centrifugal stresses on that blade.
This is a brand new factory fresh Trent 1000 engine headed for a 787 somewhere in the world, and you won't see an engine as clean and shiny as this. It's amazing. Another thing that's so cool to be able to see, especially well when an engine is in this state, is these modern high bypass engines and just how small the engine core is compared to the fan diameter. You can just see straight through here, through the blades. It's so cool to see. Really cool here getting a chance to look at these parts of the engine sort of isolated, separated from each other. This is the whole section that's going to be burning fuel and creating thrust. That's your core of the engine. Over here you have fan case, which is not just a container for the blades, actually. It also is the brains of the whole operation. So basically, over here you can see it well. This behind me, the black thing, that's an engine control unit, and that is where all the inputs from the pilots come through to the engines. Anything they want it to do goes through there. The fan case also obviously very important for containing fan blades in the event of some kind of incident. You need to be able to contain these blades that are very big and spinning very fast. So they have a Kevlar lined fan case, and the blades themselves are made of titanium, but they're actually hollow, and that's for weight saving. This here is a very specific shop for Rolls-Royce in Derby. Here they're working on the Trent 1000s and the high pressure turbines, the hot section of those engines specifically. They're brought in here from having been out on the wing, flying around the world. They're getting the high pressure turbine systems swapped out with replaced components in order to increase the durability, the time on wing, as they call it. And the idea is that doing it this way, they can get them in, swapped out, fixed up, and sent back out to the airline much quicker. That's leading to a much better picture for sort of fleet reliability for the airlines that are operating the 787s with Trent 1000s. This facility started up about a year and a half ago, and they're ramping up, so they're doing more and more of this stuff around the world. The super cool thing is that what they're doing is mostly they're improving the durability of the high pressure turbine systems by increasing the cooling airflow, drilling small holes into the hollow blades in order to keep them cooler. And this is very necessary because these things are spinning at 13,000 RPMs, they told me, over 13,000 RPMs, and they're experiencing temperatures of 1,500 degrees Celsius. Extra cool fact about that is 200 degrees Celsius higher than the melting point of that metal. And these things are running non-stop, turnaround times as quick as possible. They basically never have a chance to cool down until they have a more extended maintenance check. So these things have to be incredibly durable. And they're making these improvements in durability mostly now with that increase in cooling airflow and a slightly different coating on the blades. From what they've told me, it's really stuff at the leading edge of physics, even though it seems like a subtle minor change, and it's making a big difference to the reliability of these Trent 1000s.
This is probably the oldest building on Rolls Royce. It actually predates Rolls Royce on this site in Derby. This is and was a very old building, but hopefully as you turn around and have a look at the reveal of what this facility looks like now, we've spent a lot of money in making this now a state-of-the-art facility to incorporate the new phase 1 durability modification. As we ripped up the floor, put in new cranes, put in new gantries, brought in all new tooling, recruited over 100 people in under 12 months to bolster the workforce we've already got in Derby. We do everything in Derby from full overhauls engines have to come in on fixed intervals to have their critical parts replaced. And then we also do targeted servicing or repair. If you want to go and fix a specific issue, or there is a particular modification you want to bring into the fleet, then we have work scopes for that as well. So this shop has been set up specifically to do the work scope, which is replace the existing turbine blade with the new, more durable turbine blade. A Trent engine is a modular engine, so if you want to go and get a component out of an engine, you don't have to strip the whole engine down to get the component. It is made up of modules. So when we bring these engines in, we take off nose cone right to the front of the engine, so we can then tip it over, put the engine down on its nose, and then you can start pulling the modules out of the engine. On the left, it's covered up, but the low pressure turbine system, that's at the back of the engine, so when it's on its nose at the top, we pull that out first. Then it's the IP turbine system, so just behind you can see there's an intermediate pressure turbine system that comes out, and then what you have exposed is the high pressure system, which actually has the high pressure turbine, the combustion system, and the high pressure compression system all in a mini module. So we call that mini module. That's what this thing is here, and that is what we're going to take out of the engine to then send that to a module bay so we can do the modification in that area. So we'll walk down so you can see a few of these. We've actually got 15 engine bays that we've set up to do this work scope. So you'll see lots of them will have a fan system, and then just sticking out of the top is an intercase. That is because you'll see we've taken out the low pressure system, we've taken out the intermediate pressure system, we've pulled out the HP system, and we've sent that to a module bay to have this modification done. But then as you walk down, you'll see some engines. So this engine here is actually on build. So this has had the modified HP system brought back to the engine bay. They've put that back in the engine, put the IP turbine system back on top, then the LP system back on top of that. When that has been fully dressed, we will then tip the engine back over horizontally. We have 3 engine test beds in Derby that can test MRO, so Part 145, Trent 1000 aero engines. So we will send them down this gangway here. Through those doors, you can get a door that will take you all the way to one of those test beds, where we will run the test, make sure meets performance requirements, vibration requirements. Passes test, it will then come back to the main shop, where we will dispatch it, put it in a stand, send it around the world to customer. All the modules have been put back in, so they're now dressing the engine with externals, all the required pipe work. You see all this tape and all these blanks. That's to stop any components from dropping down. As either if you're stripping an engine or building an engine, people are holding nuts and bolts in their hands. What you don't want to do is then drop it into open orifices. So that's why you see all these blanks and bits of tape to ensure that you can't get anything into the engine. So you'll see now that they would have had to have broken all these joints to be able to remove the modules. So now before we send it back to test, we're going to have to resit all these components.
Wow.
What you can see here, this is the HP system, the high pressure system. So this is the module as part of this workscope that we're wanting out of the engine to put in the new high pressure turbine blades. And as part of this modification, there's also new fuel spray nozzles, which are these components here. So on the strip, we've stripped it down. As you walked and saw the other bays, you saw just up to the intercase just sticking out from above the fan. We will strip all these items off to get to that HP system. And because that's been modified, that has now been placed back on, then the IP turbine system, then the low pressure turbine system.
Wow.
And now they're just rerouting all the pipe work and harnesses so they can send it to test.
So you're not fully swapping out this whole system, you're swapping out elements of it.
Yeah, correct. And we'll go to the module bay in a moment so you can see how they do that. You've got some inductors here, so engines we've just recently brought in. There should be a nice spinner on the front, nose cone. That's obviously been taken off, otherwise we wouldn't be able to turn the engine on its nose. These guys, we do some induction boroscope, so we put a probe into the engine to make sure that there's nothing else we're going to find when we open it up, so the workscope is what we want it to be. And they're just removing a level of externals in preparation for when we start stripping it vertically. Is those modules we were pulling out the engines, so you've got different bits of the high pressure system here, so whether it's cases, whether it's the compressor system, those are all serviceable, waiting to be built back up into a high pressure system. But what they're waiting for us to do is of course replace the new HP turbine blades. Well, it's just been fitted, so the new standard of HP turbine blades, which has been placed on a HP turbine disc, balanced assembly and then put into the top. So over the other side you saw this bit missing, so you could see the nozzle guide vanes. That's because the disc wasn't there. Balanced disc with the new blades in it has now been placed in. And these are the seal segments the chap was just showing you that the blades run in, so you can see how it's just been dropped on top. So that's ready now to put back into the engine. The reason why we're having to modify turbine blades, and it's so linked to time and wing, reality is this is the hardest working component in the whole of the engine. So these blades run at over 1500 degrees centigrade and spin at over 13,000 revs a minute. So you can see why under those extreme pressures, temperatures, speeds, that's why regularly inspect them, and if they don't meet in-service limits, you have to take the engine off, and that's often what can drive time and wing, especially with more modern fuel-efficient aero engines. So by bringing out this new standard with improved cooling, it's better coping with those extreme temperatures, and hence why we're able to double the time and wing because of it.
In this particular building, we have just about every modern Rolls Royce jet engine that's on fleets around the world right now. They're all what they call dead engines. They're not being used anymore, they're not serviceable, they're not fit to fly. But what they do here is they work with customers, partners to bring them in and look at every aspect of how to work on, maintain, service these engines while they're out there flying around in the fleets of the world, to make sure they have all those practices down to do them properly, including over in the corner there, an XWB engine, which they use to show how to disassemble it for transport, because the whole thing in one piece cannot fit on a 747 freighter. So super cool to be able to see all these Rolls Royce engines in one room.
So what you're going to see here is a Boroscope inspection. So we're interested in looking at the maintenance of engines, how we can use that maintenance data to inform our wider fleet management and fleet health activity. We want to standardise the task. So ideally, this is a Rolls Royce solution, but the Boroscope technology, which is Waygate Technologies, is actually industry-wide applicable. So an airline could take the Boroscope kit, hardware, and then use that on non-Rolls Royce products as well. So if we can get standardisation across the industry, that helps the people doing the inspection because they're only using one set of kit, helping the inspection be carried out more efficiently, more accurately, better quality, which obviously all leads to safety and reliability. But then the generation of that data created in a standard way and moved through to cloud in Rolls Royce, which then gives you lots of opportunities around how you process that data using image processing and future AI development as well. The engine we're going to be inspecting today is part of our Intelligent Boroscope Method programme. The Trent 1000, the Trent 7000 engines are the lead engines for that programme. The method can be applied to all Trent engines, but that's our lead programme. This is Trent 7000 engine. What you're looking at in the middle of the engine is the core engine. The high pressure system is kind of in the middle here. To carry out an inspection on this system, what we're interested in is, so there'll be periodic inspection of the high pressure system, so looking at high pressure turbine blades, physical condition of high pressure turbine blades. So the aircraft maintenance manual will require you periodically to go in, carry out a physical inspection. The physical inspection process, obviously the hardware is right in the middle of the engine, so you have to get into the engine, get to the hardware, and to do that we use Boroscope equipment. The Boroscope equipment is the Waygate Technologies Mentor Visual IQ Plus, which is the latest and greatest Boroscope technology. It does quite a few novel things. Access through a fairly small port which is on the side of the engine. Is that the open port? So the Boroscope has a long lead and a camera on the end of the lead. So effectively you are able to, and this lead is, you can articulate this lead. So this lead has wires in it. So effectively there are motors in the Boroscope that will pull the wires. We'll be able to show you this actually. Yeah.
It's a 6.1mm probe with a side-facing tip. I'll keep the light away from the camera to try and... So we can use that by going into the engine and directing it. So if you're not on a straightforward part that the engine is easily accessible, you can navigate that through the different stages to get some.
So he's kind of making that look easy, but when you're trying to feed in the probe, you're not entirely sure which way you might be facing. So there's lots of degrees of freedom when you're manipulating that probe to try and get to a certain location.
I see.
He's made that look very easy, but that is actually quite hard. So there are other technology programs that at the moment we're working on might help you get there, whether that's robotics or whether that's automated feed systems.
Okay.
Because actually it can be quite difficult to get to a location in a controlled way. So the Boroscope tip that you can see there is a 6mm Boroscope tip. So you can see the light. So it's got a light for when you go to the engine, because obviously you need to be able to see what you're looking at. It also has a built-in 3D projector. So it projects a grid of structured light onto the component that you're looking at, which effectively enables you to get a 3D scan of the component. So there's some really amazing technology in the tip of that probe, which has been miniaturized. So we've got a camera, a 3D scanner effectively, and a light source, all on the end of this articulating control.
Wow.
And that's what makes this Boroscope technology more unique, that you are able to do this 3D scan. So now we're in the engine, we've articulated the probe. Craig's operating to control this to a fixed view. So we've now published some fixed views for the AMM engine maintenance manual. So we now have a fixed procedure for the operator to follow. So the operator will now put in some metadata. So really important that we tie physical engine, physical inspection date, operator of the engine with the visual data, so that when we move all of this data back to cloud, then we all have all of the associated metadata, so then we can start doing the bigger data analysis.
Right.
The airline also need that for their audit trail for when they've done the inspection. So if they're using a cloud-based platform to store all of this data, then they have a structure of who did the inspection, when it was done, whether it was a pass or a fail. It's all stored in the cloud.
Right.
So this is a process called menu directed inspection. So basically we've published, so through their app store on the Boroscope, through Waygate's app store, we've published an inspection procedure, which is a structured inspection procedure. So it takes you to the engine type, the location, and gives you the specific, there you go, gives you the specific lines that you need to operate to position and capture the data.
Wow.
So prior to this, you may have carried out the inspection as an inspector, not recorded any images, but maybe said pass fail. What we're moving to now is completely standardised menu directed inspection. So every customer uses the same kit, every customer uses the same method, every customer captures the same data in the same way with all the metadata, and all data is then communicated back to cloud. At that point, and you've got the power of the use of all of that data. But it would also improve the inspection method, because standardisation is good from a human factors perspective as well. Now the other part of the system is the Rheinstyle future drive. To inspect the turbine blades, we need to rotate the core of the engine. Prior to that, we would have to have another mechanic on the gearbox down there, and you effectively had to ratchet the gearbox round in a controlled way to get each blade perfectly positioned in frame, and then you do your inspection. The turning tool is connected to the boroscope, so the two things are communicating with each other. So now we can automatically increment round to position the blades perfectly in frame each time, and then trigger the capture process to capture the data. So that would be, how you start the engine with an air start or power off takes for electrical power for aircraft. So what you're seeing there, when I said there's a 3D scan, so it takes an image, takes a 3D scan, and it combines the image and the 3D scan together to give you effectively a full 3D representation, but it can only see what it can project light onto. So where there are some gaps, that's just where it's not able to project light. And so what you're seeing now is the measurement process. We now have a 3D scan, an image, and then the inspector can put points on and take a measurement or measure areas. So the interesting thing about this technology is the 3D data and the image are all embedded together. So if I send that data to the cloud, so I do an inspection in Singapore, send the data to the cloud, I can actually carry out the physical measurement process on the cloud in Derby for an inspection that's happening in Singapore. So once we get the system embedded in the fleet, what we will see is standardized method, standardized data, embedded 3D data, move directly to the cloud, because the Boroscope actually is Wi-Fi connected, so it can move data. And then we can integrate all of that data into our health monitoring systems, where we can do post-processing, remeasurement, and then we start to get into the AI and image processing world, where you combine those methods. And so we can look at how engines are deteriorating in different environments. So if you were in a sandy environment or a non-sandy environment, how an operator might be using that engine from a temperature point of view or route structure point of view. So it integrates with all of the other data about the movement of aircraft around the world, the movement of which route structures they may be operating in, the environments they may be in. You may want to integrate weather data into that. Our health monitoring system has pressures and temperatures and speeds, which are all communicated back to cloud. So you're starting to build this big ecosystem of data, all of which tells you different pieces of the puzzle in terms of how these engines are operating and deteriorating, which all leads to much, much better planning, forecasting, and customer experience, really.
And presumably also then when you're thinking about future designs and
future design. So all of this data in cloud is consumed into future design. So it may influence the current engine products by changing the design, changing the cooling hole arrangement, because when you're getting into the very specific details of where blades are deteriorating, then you can redirect things like cooling air, and then you might get into bigger architectural changes around the engine if you feel that is appropriate based on the service data. So yeah, that's probably its highest long-term value, which is getting it into future design so that the future design's much, much more improved. And so this we're looking at the fan blades. So fan blades, bulk of the air moved by a jet engine go through the bypass, and that's where the majority of the thrust comes from, about 70% of the thrust. So these fan blades are working incredibly hard, a good chunk of the 70,000 pounds of thrust. From the facts, I guess, through the development programme, these things are incredibly rigorous. So we do things like bird ingestion, where we actually, via the weighted equivalent of birds in gelatin at blades. We also have to be able to contain and manage fan blade release. So we physically run an engine at full power and blow the fan blade out of the route, and the engine still has to contain that debris.
Yeah,
so
amazing.
Incredible. Some of the development testing is incredibly expensive, single test to write an entire engine off, but for safety, it absolutely required and certification. So.
Ready for some fun facts about these engines, and all of these I learned today. Okay, so first of all, Rolls Royce, known for these spirally things on the spinner at the front. What I never knew before was where that line ends, that indicates where fan blade number 1 is. So that's really useful in the maintenance process. Second really cool thing, this is a patented aspect of Rolls Royce engines. You have a rubber tip at the end of the spinner, and that is so that ice forming on the tip, which that's where it forms first, gets broken up and dissipated before it spreads across the cone and into the fan blades and potentially causes problems and damage. Number 3 of cool things that I didn't know, Rolls-Royce engines spin clockwise as you're facing them, and that's unique to Rolls-Royce. That's something you only get with a Rolls-Royce engine. Finally, and this is the most detailed, nerdy, geeky aspect of all, if you're looking at an XWB engine, you want to know which one is the 97K version, which is what you'll see on an A350, you can tell because it has these aerodynamic features right at the base of the cone here. So if you're ever looking down at your engine and you don't know which airplane you're on, I don't know how that would happen. you could check out these things and you'll know. Little raised bits, that will tell you that it's the 97K version. You can impress your friends, or maybe not, depending on what your friends are into. You can at least convince them that you are very knowledgeable, maybe a little bit nuts, like a lot of us are, right?